All right, so this is the retake for the first of the exponents quizzes. It covers exponential, or rather fractional exponents. It covers some basics of numeracy, square roots, cube roots, those kinds of things. We really can't move on until everybody gets 100% on this, the first quiz. So I'm starting off here with a question that's about fractional exponents, and you can tell what I mean because this here, 1/2, is a fraction. The fraction 1/2 is the same as the inverse of square. So in other words, square would be 2, and 1/2 is the inverse, which is a square root. And then the square root of 64, it's the opposite of a square. 8 times 8, or 8 squared, is 64, so the answer here is 8. In other words, the square root of 64 is 8. Now this one is the cube root of 64, and you recognize that by putting a 3 on the outside. You're answering the question, what number is inside 64 3 times? So that's the same as the fraction 1/3. So 1/3 is a square root, 1/2 is a square root, 1/3 is a cube root. And then the next one down on the list is going to be, let's see, probably, yeah, here, 64 to the 1/6. The reason I picked that one is it's the only one that has a whole number. The 6th root of 64 is 2, and that means it's the 6th root, which is here. And then we only need to know what goes into 64 3 times. So what times what times what gives you 64? And the answer is 4. 4 times 4 is 16, and then 1 extra 4 is 16 times 4. So that gives you 64. So that's number 1. All right, next question, and you can see what I'm talking about. Each one of these is just a basic understanding of what exponents are, which is really kind of sophisticated because an exponent can do a lot of things. It can multiply, it can divide, it can give you a square root, it can take a reciprocal. There's a lot of confusing things that an exponent can do. All right, so this one, 5 to the 0, it means there's no 5s at all. You left it alone. So if you don't times it, you don't divide it, it means you just leave it as 1. The next one, -1, means that the count of 9s is 1, so there's 1 9, and the negative means you're dividing by it. All right, so you divide by 9 once. 1 divided by 9. The next one, a fractional exponent, in this case 1/2, a fractional exponent means square roots, so that's the square root of 49, which is 7. And then this is the one that's difficult. A lot of people wanted to say 4, because they know that the square root of 16 is 4, but this isn't asking for the square root. What number is in 16 4 times? And if the answer was 4, it would be 4 times 4 times 4 times 4. That's way too big. The number that's in here 4 times is the number 2. 2 times 2 times 2 times 2. All right, this next one, we're looking for a bunch of different scientific notations. So I'm going to start with the numbers. This one is 6 million. A million has 6 zeros after it. So I'm looking for something with 6 zeros, and this one has 6 zeros. So in other words, that's 6 and then 6 zeros after it. So 6 times a million. The next one, 9, is 9 times 1. And if you don't do anything to the 9, that is, if you don't raise it to any power, it's just times 10 0 times. So in other words, you left it alone. 9, and you times it by 10, no times at all. You left it as 9. And then this next one, 114.8, I moved the decimal 1 2 times. So that means I want to make it 2 times. Okay, so this one, I moved the decimal between the 1 and the 1, and then I moved it to make that happen 1 2 times. All right, so that's the count of how many decimals I moved. And then the 10 to the second power is the same as 100, so I'm going to put that there. All right, so move the decimal 2 times, and so the count was 2 right here. Now this is a little bit more difficult. 1 divided by, this is a negative exponent, so I'm looking for a negative exponent. Yeah, this one. You divide it by 10, 1, 2, 3, 4 times, so it's 3 times 10 to the negative 4. And I'm dividing by 10, so that's a tiny, tiny decimal. So where is the tiny, tiny decimal? It's right here. Just to double check, let's count the zeros. 1, 2, 3, 4. Yep, I divided by 10 4 times. Here I divided by 10,000, and here I divided by 10 4 times. This is probably the most difficult question on the test. I need to rank these from least to greatest. So to start with, I'm going to look for the smallest number here and put it over here. And let's see, I've got, this is a negative number, so a negative number is always less than 0, so I'm going to put that there. None of these other numbers are negative. This one is 10 to the second, that's 100, so that's going to be the biggest number. All right, so now I've not got to look for numbers. It looks like 0 is going to be the next one, because all these other ones are positive. Okay, so a negative, and then 0, and now let me start for looking for small positives. This has 1, 2, 3, 4, 5 zeros, so that's 10 to the negative 5th, and this is 10 to the negative 3rd. So this is going to be a little bit bigger than this decimal. So here, and then here. And then 10 to the 0 is 1. All right, so let me double check those. I've got negative 10, then 0, then a small tiny decimal, and then a slightly smaller tiny decimal, and then the number 1, and then the number 100. All right, so this is basically a proof that of the property that you can add the exponents. So in other words, 1 plus 3 plus 4 should give me 8 at the end. This is a proof of that. So first, I'm going to take and I'm going to expand out 3x to the third. I'm going to write down what that means, x times x times x. So that's called expanding. And now I'm going to switch the order. The 5 was here, and I'm going to move it all the way up here to the front so that it's next to the 2. When you switch the order of things, that's called commuting. And this is the weirdest one. When you put parentheses around things, that is, you group things together if they're in the same family. So the 2 and the 5 are in the same family, so I group them together, and then all these x's are in the same family, so I group them together. And your family are called your associates. And then this is what was the point of this? This was a proof that this expression, you could add the exponents 1, 3, and 4 to make 8. So that's what I've got right here. So if you times the numbers in front, 2 times 5 gives you 10, and then 1x here, 3x's here, and 4x's here is a total of 8. Before I started this one, I had to think about it for a while because there seems like there's an awful lot of information in this question. But then I'm going to look at the question options, and it just says writ in scientific notation. So these are actually all equivalent answers. This one and this one is a little bit different, but they're basically all the same. But the only one that's in scientific notation is where you pay attention to the first number only and then count the digits after that. The actual number is this number here, but the only one of these that's written in scientific notation is this one here. So you actually didn't need to think about anything. The only one of these answers that's in scientific notation is that one there. All right, for this one, we can't use our trick of just looking for scientific notation. There's a really tricky thing that they did here, though, about the closest. What they're trying to get at here is, in scientific notation, the most important thing is that you've got the place value right. In other words, it's closer to say that you have $1 billion than when you really have 2 billion than it would be to say that you have 2 million. Okay, so it's more important to get the billion right than it is to get the 2 right. There's a really tricky thing they're doing with the word closest here. Okay, so let's see. Each of these things is 2 to the 30th bytes. All right, so that's a very big number, but I don't have to worry about it. It's 2 caret 30. And this horrible number is the number of bytes that's in each gigabytes. But it says in each gigabyte there's this many bytes, and there are 40 gigabytes of memory. So there's 40 of these things, so that's times 40. So it's 2 caret 30 times how many gigabytes there were. So this was 1 gigabyte and there's 40 of them. So that makes a total of this number here. Now, remember what I said about them being tricky. Incidentally, this number is so big that the calculator already gave it in scientific notation. It's 4.29, and this E here means times 10 to that. So it's 4 with 10 digits after it. Now, you might want to pick this answer here because you're focusing on the 4.29. Don't do it because it said times 10 to the 6. That means 4 million. It's not 4 million, it's 40 billion. And it's more important to get the 10 right here than it is to get the 0.29 right here. All right, so tricky question. The answer is this one here because it gave you the correct number of digits after the 4. All right, it says to evaluate the expression negative 4 times x to the third squared for x equals negative 5, you would first multiply negative 4 times 2. This is something that's a little bit tricky. The negative 4 here is a coefficient. That is, it's just a regular number. So if I read this and I skipped the x to the third, I would say negative 4 squared. Now, negative 4 squared is not 4 times 2, it's 4 times 4, so this is false. And this is a good example of why that worked, why this was not, for instance, this is not 3 times 4 to make 12. So this is, they're going to expand it so that you can see why that is. So 3x squared to the fourth means 3x squared a total of 4 times. So the 4 here is the count of how many x squareds there are, 3x squareds there are. So another way of writing that, let's count the 3's. There's 1, 2, 3, 4 3's, so that's 3 to the fourth. And let's count all the x's. We need to be careful here. There's 2 here, 2 here, 2 here, and 2 here. So it's 2, 4, 6, 8 x's. So that's 3 to the fourth times x to the eighth. Now 3 to the fourth is the same as 3 times 3 times 3 times 3, which is 9 times 9, or 81. And so I'm going to put the 8 here. All right, so what they're going after is this number in front, the coefficient. 3 to the fourth you do not do 3 times 4. So it's 3 to the fourth, which is 81, but you do 2 times 4, because the exponent is just the count of how many x's there are, there are 8. All right, we're continuing our game of expanding expressions in order to figure out what they are. This is fractional exponents 2. It's the very last assignment that you get. They've split 2/3 into two fractions. 2/3 is the same as 1/3 times 2, because it's 2/3. It's 2 1/3. All right, so I'm going to do this 2 steps at a time. 1/3 is the same as a cube root. So the thing that's in 125 3 times is the number 5, because 5 times 5 times 5 is 125. And then I square it. So my final expression is 5 squared, which is 5 times 5 is 25. Okay, 2 of these just apply the basic rules of exponents, and one of them I'm going to put into a calculator. When I'm timesing 2 powers, the rule is to add 2 plus 7 to make 9. When I'm timesing 2 powers, in other words, when you see a parenthesis, when I'm raising a power to a power, or in other words, when you see a parenthesis, you distribute the 4 to the 3. 3 times 4 is 12. Okay, so here you're adding the exponents. The rule for multiplying 2 powers is to add the exponents. The rule for raising a power to a power is to times the exponents. And 9 to the 3/2 I'm just going to put in the calculator. So that's 9 caret 3/2, but I need to make sure that 3/2 goes in parentheses, because otherwise the calculator won't do it in the right order. It's 27. The reason is that the square root of 9 is 3, and then 3 cubed is 27. Got another proof in which we're going to try to prove, the point of this is that 9 here minus 2 here makes 7. So that's our objective. What I do is I split out. I've got 9 x's on top and 2 x's on bottom. So I'm looking for the problem that has 9 x's on top and 2 x's on bottom. This one has 7 x's on top. 1, 2, 3. Oh, sorry, this one has too many, I think. 3, 6, 9, 10. Okay, this one had 10 x's, and that's the reason it's wrong. This one has 9 x's on top and 2 x's on bottom, so it's right. Sorry, I left it highlighted. I picked this one, but I didn't highlight it right. Okay, I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9. The correct expanded expression for x to the 9th is here, and that's the reason why this one is the right one. All right, this one says, as Jose thinks about his old MP3 player, and this is old because it's only 512 megabytes, he wonders how many songs 512 megabytes can save. If the average song contains 3.5 megabytes, how many songs can be saved? For this one, you're going to need to divide these two numbers. Basically, if you think about it with money, if you spent $500 on cheeseburgers and each cheeseburger was $5, it's obviously you would have to divide because you could buy 100 cheeseburgers. The only thing that I can see that they're trying to break you of the habit is paying attention to these decimals that don't mean anything. So it's kind of in the vein of scientific notation that all the decimals on this become less and less important as you go through. So it's approximately 146 songs. All right, so for this one, I'm going to need to write this stuff down. It says, here's another real-life problem. In a year, there's 1.6 times 10 to the 8 vehicles and 1.12 times 10 to the 11 gallons. And it wants gallons per vehicle. Okay, so let me write that down, what it is that we want. We want gallons per vehicle. Okay, so that tells me what it is that I'm trying to divide. I'm going to divide the gallons by the vehicles. So let's figure out the number of gallons. So that's 1.12 times 10 to the 11. 1.12 times 10 to the 11 gallons per how many vehicles. This is a good example of, this number is actually hard to figure. Okay, it's 16 million. No, 160. This is 160 million registered vehicles, and this is a huge number, just a little bit less than 1 trillion gallons of fuel. So that's an example of the kinds of calculations that scientific notation makes easy. 1.6 times 10 to the 8 vehicles. And that's only half of the problem. So now I'm going to have to treat this as two separate problems to do. I've got the numbers in front that I need to handle, and then I need to subtract these exponents to keep track of how many digits there are after. So I'm going to do the first part.